Thanks. All right, so today I'm gonna be talking a little bit about Scribble, which is also a tool to do security things around smart contracts, but it's gonna be a little bit more custom than what you would do with Slither. Um, but before I dive too deeply into things, I'll give you guys a little bit of background on myself. I'm Joran. Like the most simple way to describe myself is that I'm a security nerd. So by day, I'm the product lead at ConsenSys Diligence, helping like building and publishing tools such as Mithril, MythX, Vertigo, which is a mutation testing tool, and more recently, Scribble and Diligence fuzzing. And Scribble is going to be the main topic of today's talk. By night, I like to do some bounty hunting, and you might know me from Twitter, where I post some nice essays and threads on fuzzing and Web3 security type things that I personally think are interesting. Um, Yes, let's see. To talk a little bit about the structure of today's talk, I have given several talks on Scribble before that are kind of introductory. Like I go through various examples and simple properties and go through what they are and what they look like and how you build them. This talk isn't going to be like that. So I'm going to do a really, really short introduction into Scribble, tell you a little bit about what it is, what it looks like, but then we're going to dive right into the matter. And I'm going to show you actually like how I apply this tool in my workflow, or like how I use this tool. So we're going to go through my process, and then we're going to actually apply it to two like real world examples, Uniswap VT2 and an ERC20 token. And then towards the end of the presentation, I have two topics which are kind of like these topics that come up when you start to do some advanced scribbling. It's like, and they'll give you a little bit of background in things that you might do when you use Scribble yourself. Right. Something is going wrong. That's weird. Okay, it's working now. So Scribble is a specification language at its base. This means that it's a language, like it's kind of like a programming language for writing specifications. Like you essentially define the behavior of a smart contract in this language. We use it with a technique called runtime verification. So what we do is we take the specs in the specification language and we translate it into runtime checks, so that when you run the same code, it will trigger proper like these event emissions whenever one of your properties is violated. And this enables something really cool, namely property-based testing, because what we can start to do is either run unit test or fuzz test that automatically cover the code base and that potentially trigger these property violations, and they will tell you essentially if there's a vulnerability in your code. That's kind of abstract. So here's a really short example that we'll also see later in this talk of what such a Scribble specification looks like. So you essentially write this inline documentation that's mostly based on what Solidity looks like itself, but with a few tweaks. So in this case, we have function annotations called if succeeds, and they say something about what should be the case in case when the function actually runs successfully. So it might revert, in which case we don't check the properties, but if it doesn't revert, then these properties must at least be the case. That's it for the super high level Scribble intro. Now for the process. And this process might actually look a lot like the process that people use when doing normal security reviews, because I know from a high level it's pretty similar. So the first step is like pretty straightforward as well. You got to learn about the system before you can accurately describe using a specification language what code is supposed to be doing. You got to understand what the code is supposed to be doing yourself. So you got to learn about the system, figure out the functionality, like what is it trying to do? Is it a landing platform or whatever? And then the next step is to figure out how it is actually doing or providing that functionality. The good news is if you are building smart contracts yourself, this step is super easy because you will already know like how your own smart contracts are supposed to be working, or at least I hope you do. Um, Once you have a good understanding of the code base, the next step is to prioritize the elements of the code base that you want to focus on first. In the end, we don't want to spend days or weeks like wasting time on writing properties that won't cover any critical behaviors. We want to focus our time and be efficient. So I've written down 3 prompts here that kind of guide you towards the right elements of the code. So these are kind of centered around one, the central functionality, like what is the code supposed to be doing? Then two, the core assumptions that other people will make when integrating with your code. And I say other people, but I kind of include yourself in these other people too, because you might write code that interacts with your own code that has like cross-cutting assumptions. And then the last prompt is more important for larger code bases. And so today it's also not going to be a good prompt because the 2 examples that we're going to look at are relatively small. But it usually makes sense to focus your efforts on the elements of a code base that actually hold a lot of funds or that have a lot of risky operations in them. If you just have a smart contract that doesn't do much interesting or risky things, then you won't get a lot of added value by writing properties for them and eventually fuzz testing them. So once you have essentially gone through these prompts and figured out essentially the important parts that you want to focus on, that's when you can get started writing some properties. So enough talking. Show me the code. Let's try it. So the first example that I have here is going to be Uniswap v2. And I'm going to guess that most of you are familiar with this system. And we're going to try to answer these 3 questions. But the first thing that should really jump to mind when you hear Uniswap is constant product AMM. So the core thing or that Uniswap pioneered here is this idea that you can have an automated market maker that uses a constant function invariant to facilitate trades. And so this is kind of the core, and they already use the word here, invariant. This is kind of the core assumption of this system, that there's this invariant, namely the constant product, which says that, well, if I take like a Uniswap pair has 2 tokens, it has balances in both, and the product of that can't decrease over a swap. So that will be our core assumption. The core functionality is simple. Uniswap AMM, what it does is it facilitates trades, but it also facilitates liquidity provisioners, like so that they are able to get some yield out of their assets. So those are 2 core functionalities for the system. And then lastly, to look at the code with the most risk. So Uniswap has a few components like a factory, a pair, a token, and definitely the smart contract where all the interesting logic is, where all of the money gets moved around. That is the pair contract. So when we write annotations, we should focus on this. And let me stop sharing this window for a minute and move over to VS Code because I'm going to show you some properties. So this is actually or a lot of the properties that I'm going to write are already available on a Git repo, and I'll share the link to that after this presentation. So moving over to my VS Code. Yes, everything is working correctly. So I have the Uniswap V2 pair open here. There's a lot of variables, a lot of logic, and you already see that I added some annotations here to some of the functions, but I deleted the ones for the interesting functions that we're gonna annotate today. So let's start with the beginning where I mentioned this score invariant, like the constant product invariant. This is the invariant that must hold when you do swaps. So if you scroll down a little bit to go to the swap function, it should be right here. We can start writing properties by adding annotations right on top. So let's write in if succeeds here because we want to say, well, this swap function is allowed to succeed if it satisfies the constant product invariant. And we can measure the constant product or the product of the two reserves really simply by doing this. Reserve 0 times reserve 1. But really what we want to say is that we want to compare the state before to the state afterwards. So we want to say, well, the old product of the two reserves is equal to the new product. And well, some of you might already know or notice that this property is actually not correct because you are completely within your rights according to this contract to dump whatever money you want into the system as long as you increase the constant product during a swap. So you can actually, the system is okay with you taking really bad trades and giving the system a lot of money for free. And so the property is actually that there's no constant product, but a strictly increasing product. And this is essentially our core assumption, that the system validates this core property. And now we can dive into the functionality of the system. Again, one of the core functionalities of this system about swapping assets. The other is about providing liquidity. But since we're looking at the swap function, let's go for a property here first. And the property here is going to be super simple. I want to say, if you look at the interface here, you see two variables, amount out, amount 0 out, and amount 1 out. And we see here that they are transferred out to the to address. So we can say something here like we gotta take make this interface all right, but we have token 0 and we take the balance off the to address and we add the amount amount 0 out, and then we say that it's equal to that balance. And now we gotta add that like timing element. We want to say that, well, here we don't want to measure the value afterwards, but the value before. So essentially what we're saying is the to address receives amount out of token 0 and a little bit of copy pasting, the best skill a developer can have, or an auditor really, gives us the other property. And again, some of you might notice that this is not correct either, because you can do this flash swap thing. So in some cases, we actually get to return some of the funds and pay fee over that. But we know that essentially this property only holds whenever we don't submit any extra data to it. So let's encode that as well. If it's 0, so if we're not providing extra data that will cause a callback, then we know that we should get the balance added. And the thing here as well is, if we do provide data, then essentially the swap function doesn't really care about the resulting balance of the two addresses. There's no guarantee that this code gives, and also no guarantee that our properties should essentially encode that the recipient, being the two address, will receive any tokens in that case. And so the way that Uniswap actually works is they delegate this responsibility of checking that all the balances work to a periphery contract. So that's also where we would write our property saying, or where we would write these properties saying that, well, if there is this data length provided, then that higher level periphery contract would be the party responsible for checking the properties, those additional properties. So that encodes our swap function. Let's quickly dive into the mint function. Gonna speed through this a little bit, and write another if succeeds. So the simplest property that you might come up with when you read this is you probably want to say something like, well, reserve 0 divided by reserve 1, which is essentially the price of this AMM, is equal, or between transactions, so before and after adding liquidity, the price of this AMM shouldn't change. That's actually not true again. So as you see, like writing properties, it can be a very iterative process. And you might find that this property isn't true by just reading through the code, or by running a fuzzing campaign that will find a property violation and it will tell you something is wrong. And in this case, it would be the property. Because you're actually allowed to give too much money to the mint function. It won't really care because it gets free money after all. So what it does care about is not giving too much money away. So to write a property about like not giving too much money, we got to have some intermediary measurements of the ratios that we're providing, like what percentage increase are we giving to both of the reserves. So gonna do a little bit of copy pasting again. I'm saying, well, the ratio that we're increasing the first reserve with is gonna be reserve 0 divided by this. And doing a little bit more copy pasting, the ratio that we're increasing reserve 1 with is going to be this. And now then we got to also talk about the amount that we're getting out of this function, which is this liquidity variable. It's returned by the function. We can measure it through the balances, but let's just use this value because it's going to be easy. So we want to say that liquidity, or the liquidity that the minter gets out, is smaller than both ratios relative to the previous liquidity. So we can do that this way. Alt, let's see, and we can exit it like this. Total supply. And we also want to match the other one. Cool. But you'll see again, this property isn't complete because there's a weird edge case here in case the total supply didn't have anything. So we can say total supply, if it's not 0, if it exists already, if it's not being initialized, then this property must hold. And so now we have this simple property that says, well, you can increase reserve 0, or like the token balance of this contract of token 0, and you can increase the token balance of token 1. But we're gonna essentially pick the worst ratio increase between the two tokens, and that's gonna be used to give you the liquidity for this contract and nothing else. And you'll see if you look at the code, that's actually being handled by this line, which takes a minimum between the two ratios as well. And now what we can do is run instrumentation here using the Scribble tool, run some fuzzing, and it will actually make sure that this check that's comparing the two ratios is actually implemented using this code. All right, let me now quickly jump back to my presentation, because that was what I wanted to show you around the Uniswap contract. So now I want to have a look at the ERC20 contract. We're going to go through the same three problems. What's the central functionality? What are the core assumptions? And where's the most risk? So first, functionality. This one is an open door, maybe again. So the functionality of a token is going to be super simple. It's you want to transfer tokens, and also you want to allow other people to transfer tokens for you. So this includes a transfer from and permissions and allowances. The core assumptions are pretty interesting here, because the core assumption, the first core assumption is that the total supply value variable is in sync with all the other variables in the contract. Other systems won't expect these to go out of sync. For example, that there are 10 tokens while the total supply is set at 5. That's a situation that should never happen. Another assumption that will depend on the specific token, but that people will have, or that your own code might have, is that a particular token is inflationary, deflationary, or that it has a constant supply. The final prompt, like I said, is going to be a little bit less interesting here, because really the contract is small already, so there's no like way to reduce the attack surface, because it's one thing already. So again, let's have a look at that and look at the token implementation. Over here. Cool. So let's start with these high-level assumptions again, because they will be super easy to describe using invariance and contract level specifications. The first, oh, let me not write a typo. The first property that I mentioned was that the bookkeeping was all right, and I specifically was talking about the total supply being in sync with the balances array. And what we want to say is that all the balances, when we add all of them up, it's equal to this total supply variable. And using pure solidity, this would be pretty difficult, but in our case, we have the power of Scribble, and it gives us this really awesome function, essentially, called unchecked sum, which we can give the balances mapping, which will instrument a whole lot of logic to be able to measure the sum of the balances. And now we have, and this allows you to get this super simple property that captures that core behavior. The other behavior is, let's talk about, okay, does it work now? Cool. Okay, so for those of you watching, not seeing the private chat, is apparently the sharing the screen was broken for a minute there. Apologies. And I was just trying to figure it out. Okay, so to recap a little bit then, here I have a property that compares the total supply value here to the sum of the balances mapping, making sure that they are in sync. The other property that I mentioned is around inflationary, like the total supply over time. So in this case, we're going to have to use an if succeeds property. This describes how things are allowed to change. And we're going to say in this case that the token is either has a constant supply or that it is inflationary using this statement. Total supply is smaller than. So this property says, well, after every transaction, the total supply is the same or larger, and this will allow any inflationary token. We can also make it a constant supply like this. In deflationary tokens will be a little bit more difficult because you want to usually define very strict parameters around when things are allowed to increase and decrease. So a global is-succeed property might not make sense there. But in this case, we essentially captured our two core assumptions in these properties here. Then diving into the core functionality, and I'll only have a look at the transfer function here, not the approvals, because it's very similar logic. In this case, we're talking about a function again, so I'm going to write a quick if succeeds property. And really what the transfer does is really simple. It just updates balances, and it takes value from me sending, and then it gives you value as a recipient receiving party. So I can write that using old again. I can say, well, I've got this mapping with the balances, and your balance plus your old balance plus the value will be equal to your new balance. But if I'm sending tokens to myself, that's not the case, of course. So it's not equal to 2. So I'm gonna write this like limiting implication. Similarly, as a sender, I'm gonna not receive the value, but I'm gonna lose it after this too. And then to wrap it up, we need one more thing to talk about this. When I'm sending tokens to myself, nothing will happen. Yep, that's it. So now we have the core functionality of the transfer. We can do the same for approvals and then the transfer from, but you see there's the properties look really similar, but there's a little bit more logic going on around making sure that the right approvals are in place and that the right bookkeeping is being handled for these properties, for the variables related to approvals. And that's really like all you need to do for an ERC20. This is decidedly a simpler case than the Uniswap example, but it does still highlight the way that you can go about these things, going for the core assumptions with invariants and these high-level properties at the top of contracts, and then talking about specific behaviors using these if succeeds properties. And going back to my presentation again, hoping that it will actually share the screen correctly this time. Giving it a second. Yes, it should work now. Cool. That's the practical part of this talk. I now want to go into two more, not philosophical topics, but meta topics really to using Scribble, and specifically the first topic is gonna be in relation to fuzzing. So if you are interested in fuzzing in the Web3 space, you probably have read a little bit about these tools. So these are the open source tools that use a very particular way to set up fuzzing. And the way that you set up fuzzing here is what I would usually call almost a type of fuzzing harness. You essentially write in code a type of entry point into the program that guides the fuzzer in performing particular steps. This can be super useful if you want to like expose essentially private functions to the fuzzer. If you want to explore really custom scenarios, like you do an approval and then you do a transfer from, and then you set up an auction, and like a very long sequence might be really difficult for these fuzzers in particular to figure out. And this way you get to trigger very custom scenarios, and you get to do really focused campaigns. A quick note here: if you use like a gray box fuzzer, like we have a diligence fuzzing, you won't have a lot of these issues. But using a fuzzing harness can still be great because it affords you the power to really focus the fuzzer into what it's supposed to be doing. But what I really want to say is that Scribble is really useful in this context. And to show you what I mean by that, or to explain that, I'm not going to make any arguments, and I'm just going to show how you can use Scribble together with a fuzzing harness or a fuzz test case like you have, for example, in DevTools. So this is a documentation example that I just did a little bit from the DevTools documentation. So this is a really simple property-based test, actually, that checks whether this function withdrawn has or meets this property that the amount is added to the ETH balance of the sender. And this is actually like we just did the example of the token. It's something really simple that is really easy to define in Scribble. So what we can do actually is we can remove this check from the harness and move it into Scribble, where it is incredibly easy to write and read. And it's actually next to the code describing what it's supposed to be doing. So it's actually much, much easier to make sure that it stays up to date when you like adjust the code. And what we can now do is like we can run the instrumentation, then the fuzzing campaign, and it will just work. What's even cooler is that you can add properties like this, and your test withdrawal harness will essentially still guide the fuzzer to checking this function, but now both properties would be tested. So the second property is one I came up with at random. Basically, I assume that a smart contract with a withdrawal function has some kind of balance keeping. So, and I assume that if you withdraw amount, that balance gets subtracted by amount somehow. So this property essentially says something about the internal bookkeeping of the example contract. And that's really it. So you use the harness to guide the fuzzer into like which actions it needs to perform and how it needs to perform them. And then you can use Scribble in addition to actually formulate the properties. And in some case, you would still reach for writing your test case completely in Solidity. I won't argue that would be useful sometimes, but in a lot of cases, there's this beautiful synergy between the two techniques of doing property tests. Cool. The second topic, let me update the page. The second auxiliary topic that I wanted to talk about today is the like software design topic, and I realize this can be like a contentious topic a little bit. But what I want to talk about is changing code so that it becomes easier to fuzz them. And yeah, so this immediately raises the question: should you even do that? Should you change code so that the security tools have it easier? The answer is maybe. In some cases, the answer is a definite no. If you are an auditor and you're auditing a project that's supposed to launch in a week or two, it's not an option. If you want to change the code in very esoteric ways that it becomes much less readable and less functional, and also that your analysis tool has an easier time at analyzing the code, the answer is no as well. But what the argument I want to make here is that there's a range of things that you can do in terms of code design that first make the code more readable and understandable and better, like from a lot of philosophical, like code philosophical perspectives, but that also make it easier to write properties for and to do fuzzing for. And so there's really one concept that I want to talk about today, and that's the first concept of the solid design principles, and then single responsibility. It's really simple. Instead of having one function with spaghetti code that does literally everything, you split up everything such that every function or class in legacy development has their own isolated behavior. Nothing should be doing two things at the same time. What's nice about this is that we get to write properties around every single behavior and every single function, and we get to describe them in isolation. And these properties end up being much more simple and concise. What's even more nice is that we can also fuzz every little function in isolation, or developers can do this, making sure that at least they in isolation are correct. And then afterwards, we still have to tie everything together, probably in an overarching like orchestration function that calls everything. But we get to focus there on writing properties that talk about the global behavior and that ensure that the global behavior is correct. So we essentially split things up, and it's not just better for fuzzing in this case or for writing properties. It's better because you also get to reason about things in isolation, and brains are just not that good at putting too many things in your brain at the same time. This is kind of a limitation of our working memory, and essentially your code will become easier to think about too. So there is this final design principle that I want to quickly highlight that has been really popular in formal verification, and this is the design by contract or the use of code contracts. And this is kind of a confusing name in this space because smart contracts. So code contracts are not smart contracts. The way to think about this is really a mental model, is that every function, every class essentially has a contract that they sign and that they promise that they will adhere to. So everything calling into a function can assume that whatever this contract says is correct and that the function will do exactly that. And so this contract takes the shape of annotations, if succeeds annotations, for example. So you go into your code base and you annotate each function describing the contract that it adheres to. And then the idea here is that if you write these functions that or orchestrating functions or other functions that use it, you essentially get to assume that that contract is true. And the nice thing is we'll instrument those properties, so we actually know during a fuzzing campaign that, well, the code contract is either true or the fuzzer will find a property violation. So this gives you a really nice way to abstract and separate properties so that it becomes super easy to write them. And that's it. Let me make sure it renders correctly again. So the main takeaway out of all of this is one that I didn't mention before, but Scribble is free and open source. It probably works with virtually every tool out there because it inserts runtime assertions. And most of the tools check for those. You can find it on GitHub, but a quick Google should probably also work. If you want to get a more basic introduction into Scribble with some nice workshop examples that you can go through, last year actually at the same conference, I did a workshop. I believe that's on YouTube, so give that a watch. We also have a bunch of material around Scribble and fuzzing on the Diligence blog. And I do post on Twitter a lot about fuzzing and Scribble and techniques like these that you can use to, well, find bugs or make your own smart contracts more secure. And that's it. Thanks.